Data processing. There is a lot of data stored, collected, and processed every minute in a computer system. Data processing is defined as the manipulation of data to create meaningful information. In addition to making data usable, when we process data, we are also looking at different interpretations of the data and how they can be visualized. Visualizing data in the form of charts, tables, pictures, and graphs helps people understand large data sets. But we'll talk more about that in the next topic. We know by now that computers like organization and structure when it comes to inputting, processing, and outputting information. Therefore, organized data is essential. Spreadsheets are one of the main places that programs like to gather input from. The spreadsheets can then be processed into databases, but for many of the processing and visualization methods of expressing data we'll discuss, spreadsheets are very useful. Programs are a common way to process data because they are capable of gathering a large amount of data as input, searching through the data to see if all of it is usable, and then clustering the data. Clustering the data means organizing the data into groups that have similar content or sources. From a set of data, programs can use looping structures to find and create new lists of smaller subsets of information. Programs have the ability to read information from spreadsheets and identify patterns or trends. There are many types of search tools available to find data. When you're beginning a search engine is a very useful tool. There are many sites that show what is trending in the world. Trending topics are ones found by a searching algorithm that are talked about the most during a period of time on a website. On many social media websites, there are trending hashtags that are used to share a common thread or a common topic. Linking ideas and information through a trending hashtag is a way that the public has found to assist sorting algorithms, although unintentionally. Searching and sorting oftentimes work hand in hand to process data. Understanding where they are used is key to developing more complex and useful programs. Data filtering systems are also important tools for finding information and recognizing patterns in data. We've written Python programs that have swapped data on a small scale, but there are many algorithms that can work with a large amount of data. How do you think the class valedictorian and salutatorian are selected every year from a high school graduating class? How do you believe those rankings are determined? As the students complete high school courses, an algorithm takes their overall average for the class and calculates any weighting advantages. The data is then submitted to a program that calculates each student's overall grade point average and compares it to all the other students in the grade. A similar type of algorithm to the one we designed that finds the smallest, middle, and largest numbers is used to compare each student in the grade's GPA and swaps the students' ordering based on the results. As we've said, computers like structured and organized data. Unfortunately, much of the data that humans provide is not neat. Gathering data easily and efficiently can be a large problem. In addition to the quantity of data that is frequently needed, a few other problems can pose challenges. Data needs to be cleaned. Data may be incomplete. Data may be invalid, and data may need to be combined with other sources. There are some types of data, like numbers, that are easily processed, whether they are integers or floating point numbers. When a data type is easily processed, that makes it easy to use in programs. Sometimes data needs to be extracted or modified. For example, let's say you are a teacher and you've decided to add 10 points to every student's test score. This might take a long time to do yourself, but a computer could iterate through the list, making these changes almost instantaneously. This is an example of transforming every element of a dataset. Perhaps you want to filter the dataset. For example, you want the computer to only show you students who received an A on the test. A computer could also very quickly compare data, like finding the highest and lowest scores on the test. Finally, a computer could easily create a visual representation of the data, like a bar chart showing how many A's, B's, C's, D's, and F's there were on the test. Cleaning data, also known as data sanitization, can refer to the modification of data that doesn't meet the formatting requirements for that type of data. An example of data that may be cleaned from a set of data would be a number that is not correctly formatted as a number and instead looks like a string. Data sanitization would revise the data to be the correct number format. A money value that is not formatted with the traditional $ and decimal format might not be utilized correctly by banking software. These are examples of data that would need to be sanitized before being used in a program. Depending on how the data is requested, users may choose to abbreviate, shorten, or provide an incorrect type of input, which would then be unusable in the program. An abbreviation or a shortening of data, such as providing initials when a user's first name and last name are requested, would be an example of incomplete data. If a user is asked for their age, which should be a number value, but instead provide their birthday, which is a string value, that would be classified as invalid data. As with data that is incorrectly formatted, data that is incomplete or invalid cannot be used in an algorithm. Sequential computing is a model in which operations are performed in order one at a time. However, if data sets are too large, and oftentimes they are, there are two other techniques that are used: parallel computing and distributed computing. Parallel computing involves breaking a program into multiple smaller sequential computing operations, some of which are performed simultaneously. Distributed computing uses multiple devices to run a program. Once the task is completed, each system submits their results and they are compiled together. We can compare the efficiency of different solutions by comparing the time it takes them to perform the same task. A sequential computing solution will take the longest time because every task is completed in order. A parallel computing solution will take only as long as its sequential tasks plus the longest parallel task. The speedup of a parallel solution is measured in the time it took to complete the tasks sequentially divided by the time it took to complete the task when done in parallel. Solutions that use parallel computing can scale up more effectively than solutions that use sequential computing, since sequential computing requires more time. However, since parallel computing consists of a parallel portion and a sequential portion, it is still limited in its efficiency by the sequential portion. Distributed computing has allowed for larger problems to be solved quicker than ever before, since the multiple devices allow for faster processing time and larger storage. Gordon Moore made a prediction in the 1960s that has guided the principles of computing innovation over the last 80 years. He predicted that processing power would increase exponentially over the years to come. This is a foundation in the electronics industry, as it has driven the need to create hardware that can support the cheaper, smaller, and more powerful processors that are needed to increase computing power. The exponential growth that Moore predicted would occur has occurred. We are reaching the stage of computer hardware development that is making the growth of computing power on small devices like phones and smartwatches challenging. We raise the topic of Moore's Law to bring awareness to the drive behind the development of hardware necessary to raise computing power and bring us into the information age. As we continue to innovate in the electronics world, the computing world will be impacted. In realizing this, and considering current work and future developments in electronics, such as artificial intelligence, we can only wonder what will occur. Will single systems of the future be capable of what it currently takes two systems to process? Will parallel processing be a thing of the past? With a greater efficiency of data being processed at faster rates, how will predictions and trending information be impacted? With a greater efficiency of data being processed at faster rates, what will the hardware look like? With a greater efficiency of data being processed at faster rates, will different mediums be used in place of hardware? Different computer systems have different amounts of storage and data processing capability. Choosing the right system based on the size of the dataset is important. With the right scale system, data should be quickly and efficiently processed to a usable state. Once usable, a program should be able to gather the necessary data easily. When we say different systems, consider the type of device you are using. whether it's a phone, tablet, smart home device, laptop, or desktop computer, and what are its storage and computing abilities. The amount of data being used should determine the system used.